So let's start talking now about in more detail about the groundwater portion of this class. So we said that water gets moved between the different reservoirs, one of which, and arguably the most important of which for many reasons, is the groundwater reservoir. And it gets there by infiltrating from the land surface down into the ground. And it's stored in pores, right? So surface water infiltrates and moves through and is stored in pores. So we think of pores as being the open spaces in the rocks, and the open spaces can take the form of fractures, the original spaces between grains, and so forth. And in general, we refer to porosity. Porosity, remember, is the percent empty space in a rock. We refer to two kinds of porosity, two types of porosity, and these are primary and secondary. So primary porosity is the porosity that exists when the rocks originally form. It's original to the rock. Original to the rock. So there are some odd examples here, like the little bubbles that form in lava as it's flowing across the land surface. That's primary porosity. But most of the time what we think of are the sediments that make up, say a sandstone or a limestone or something like that. So imagine that you've got a bunch of individual grains of sand on a beach, right? So here's some water, and these things were deposited below sea level. And they're slowly being turned from loose sand into solid rock. In this case, it would become a sandstone. So from loose sand to be turned into a sandstone. It's a process called lithification. Lith means rock, so lithification just means the process of making rock. Lithification, and it's composed basically of two elements. One element is compaction, so it gets compacted under its own weight, which reduces porosity. You squeeze those rocks tighter and tighter together. Excuse me. And then cementation. And cementation comes from the word cement. So there are minerals that form from the water that's slowly moving through the pore spaces. And as the minerals crystallize, they glue the rocks together, so the grains together. So I'll sort of blow this up now, nice and big for effect. These grains would probably actually be touching each other, but you'll get the point here. I'll put a couple of them together. So here, make it more realistic. Okay, so we've got some grains there, some big grains and some small grains. And as the water moves through this area, let's see if I can find a color. Little crystals are going to begin to form on the edges of those grains. And where do those crystals come from? Well, those are minerals that are dissolved in the water. This is akin to the hard water stains that you might find on your faucet or something, and on the side of your shower. And as those mineral grains begin to grow outward, eventually they'll start to grow together. And when they do that, they form bridges that sort of lock these grains tightly bound into and turn them into a rock. So the difference between a sandstone and sand are largely these mineral grains that have grown slowly on the edges of the grains and have intertwined with each other and have sort of glued the rock together. Well, if we zoom up even more, I'll just take a look at this up close. What we see is something that looks like this, and this, and I don't know, it looks like this, something, right? Okay, so here's a grain, and here's a grain, and here's a grain, and here's a grain. Okay, and you have these minerals that have formed in here that are sort of interlocking. Hopefully you can see this. And they don't need to fill up all of the pore space in order to glue the rocks together. They just need to take up some of the pore space. So there's a fair amount often, by the time these rocks are done forming, there's often a fair amount that is left open. And so all of this pink in here, this is porosity that exists even after this rock, even after the sandstone has turned into rock. So the pink is the porosity, and the purple are the cements. Okay, so when this rock forms, it has a certain amount of porosity that exists, and that porosity that exists when these rocks form is referred to as the primary porosity. Okay, now what can happen is that over time, the amount of porosity in a rock can be enhanced, can be increased, and that's the secondary porosity. Secondary porosity is basically are the holes that are made over time. And so how can you do that? Well, one way to do it is dissolution. So in Iowa, we have lots of limestone. Limestone's pretty soluble, particularly in acid. And you get acids at the Earth's surface when you take carbon dioxide and you react it with water, and you get H2CO3, which is called carbonic acid. And it's a weak acid, but over time, as water soaks through the soil, it picks up carbon dioxide, and then it drifts down and it starts interacting with the limestone that makes up most of the bedrock in Iowa. And this acid, carbonic acid, begins to dissolve away the rocks. And so you'll get any kind of small opening will be, over time, will be enhanced. So here's a surface, right? And let's say you have a little fracture, something there. As the water moves along it, it's going to begin to, the water will begin to dissolve the rock along those fractures, and over time, they'll get a little, excuse me, they'll get a little wider and a little wider and a little wider, and eventually they can form things like caves. One of the areas that water has a very easy time flowing along in sedimentary rocks are called bedding plains. So when you look at sedimentary rocks from the side, you often see these layers called beds. And where one bed contacts another, it's called a bedding plane. And along those bedding planes, it's sort of a zone of weakness, sort of like pages in a book, right? When you open a book, the pages don't fall apart. The pages just separate from one another along the planes that connect them. And so that's generally where water wants to flow. When water is moving through rocks, if it's moving from left to right in this case, it's going to have a harder time moving through the matrix of each bed, and a much easier time moving along these weak spots that define the boundaries between the beds. So water moves along bedding planes, and over time those can be enlarged. Of course, other kinds of secondary porosity can come, as I was alluding to earlier, from fractures, from faults, from cracks, from joints, things like that. And anyway, that's what happens. Now, in terms of the porosity, there are some factors that, particularly in sedimentary rocks, that determine how that porosity is going to go. And one of the biggest determinants of the nature of porosity is the sorting of sediments. The sorting of sediments. So we're talking about how much porosity exists in a sediment or a sedimentary rock based on the sorting of those sediments. So what is sorting? Well, all sorting it's the separation of grains by size, right? So if you were ever to go to a river and reach down and pick up the sediments at the bottom of the river, you'd probably find little bits, small rocks and little rocks and big rocks and medium rocks and all stuff in between. And that's because sometimes the water flows very quickly, and sometimes it flows more slowly. And as the water is moving really quickly, it'll carry big rocks along, small rocks and little and medium rocks all together. But when the water's flowing slowly, it'll only carry the small rocks and it'll leave the big rocks behind. the water can kind of sort out the grains by size, depending on how much energy it has. When a glacier comes moving across the landscape, the glacier just bulldozes everything in front of it. And so all of the sediments that are being pushed by a glacier are terribly sorted. They're very poor sorting. So glacial deposits, which we generally refer to as till, that's the stuff that gets bulldozed by the glaciers. The glacial deposits that get bulldozed are called glacial till. That's very poorly sorted. The opposite extreme would be something like sand dunes. Sand dunes in the desert would be very well sorted. And the reason for that is that the reason sand is piled up into sand dunes is because of wind. And wind just isn't strong enough or gooey enough, doesn't have enough energy to be able to pick up boulders and move them along. It doesn't have the ability to pick up gravel and move it along. All it can blow along is sand. And in fact, if the sand is too small, if it's like clay, it'll just get blown away and lost up into the atmosphere and never be deposited at all. So the sand dunes are extremely well sorted. All right, so what does that have to do with anything? Well, what that has to do with is this. When grains are really well sorted, this isn't going to show up very well. I better do it bigger. Do it like this. When grains are really big, you have a lot of pore space. Excuse me, not when they're very big. When they're very well sorted, you have a lot of space in between. And that's the porosity, right? But what if you were to fill in that porosity with smaller grains, right? This is what poorly sorted rock sediments look like. You have little rocks filling in the spaces between the big rocks. And then if we were to zoom in even closer and look at those small rocks, like right here, right? We've got the small rocks here, and you might even have, let's see if I can do it in purple, some smaller rocks filling in those spaces, right? So in general, what we would say is sorting is inversely proportional to porosity. Okay? Anyway, something to keep in mind about porosity.